In Tableau 2, Part 1, we talked about the card game bridge. We talked about what constituted a bridge hand, and we computed combinatorial possibilities for such a hand. Let's run through the idea of a bridge hand again. So the question at hand is the following. We're going to deal a bridge hand from a standard pack of 52 cards. Now, in bridge, aces in the pack have a particular significance. And so the question at hand is, are aces distributed across 4 bridge players in fair and equitable fashion? Does everybody get an ace? Now, to remind ourselves, we are dealing with a pack of 52 cards. The cards are distinguished in 4 major suits called spades, hearts, diamonds, and clubs. In each suit, we have 13 cards labeled ace, 2, 3, 4, up till king, in spades, in hearts, in diamonds, and in clubs. We play bridge by distributing these cards, 13 cards a player, to 4 players, traditionally called north, south, east, and west. Now, when you distribute a card hand like this, we can attack this problem purely combinatorially by counting. I'll let you have at it. Our attack here is going to be a little different. We're going to be a little more subtle and edge up to the event at hand by a conditioning argument. Now, to do this, we first should formalize what is our sample space, what are our idealized outcomes. Let's begin with this. The sample space here, I'm going to allocate 13 cards to north, 13 cards to east, 13 cards to south, 13 cards to west. We are going to assume a random shuffle, which means that all orderings of the 52 cards are equally likely. Which means that once you do this shuffle, north gets 13 cards, east 13, south 13, west 13. And if I can tell you what order these 13, 13, 13 cards are arrived at, then you've got one bridge hand. Now, the combinatorial setting here says that all permutations of these cards are equally likely. Now, there's a mind-boggling number of permutations. 52 factorial permutations. Every permutation corresponds to an atom in our game, and the chance of that atom is 1 in 52 factorial. Now, what is a bridge hand here? Each permutation gives rise to a particular sequence in which the cards were administered. But within one player's grasp, the particular ordering of the cards makes little matter. It only matters which 13 cards he has obtained. Since there are 13 factorial permutations of the cards for each player, there are 13 factorial to the power 4 possible permutations which result in the same bridge hand. And therefore, the chance of every distinct bridge hand is 13 factorial to the power 4 divided by 52 factorial. It's still an infinitesimally small number. There's a very vast number of possible bridge hands. Now, what are the events at hand? Well, the target event is clearly the event where the distribution of the cards C1 to 13, C14 through C26, and so on, is such that in north there is an ace somewhere in there, in east there's an ace somewhere in there, in south there's an ace somewhere in there, and in west there is an ace somewhere in there. The aces of hearts, spades, diamonds, and clubs are distributed 1 per player. Now let's edge up to this target event, well, one step at a time. Now, manifestly, the ace of spades has to go somewhere. So let's target an event, let's call it A of spades, to mean that the ace of spades goes to some player. Of course, this is certain. The ace of spades is just another synonym for the entire sample space. Every bridge hand will deliver the ace of spades to somebody. Oh, that's okay. This is just a starting point. That's right. Let's define a slightly more subtle event. Ace A of spades and hearts, to mean that the aces of spades and hearts go to 2 distinct players. no one player gets both. Okay, this is clearly a sine qua non if everybody is going to get one ace. Here's a starting point. Let's define A of spades, hearts, and diamonds to represent the event all permutations for which the aces of hearts, spades, and diamonds go to 3 distinct players. No player gets 2 of these aces. And finally, the target event. Let A of spades, hearts, diamonds, and clubs represent the event that the 4 aces each go to a distinct player. Everybody gets an ace. Now, these are clearly events which are relevant to the problem at hand, but there are certain inclusions in these sets. And we can very quickly figure out what these inclusions are. If everybody gets an ace, then clearly the aces of spades, hearts, and diamonds have to go to 3 separate players. And therefore, the last event is a subset of, is contained in the event A of spades, hearts, and diamonds. But if 3 players get spades, hearts, and diamonds, 1 apiece, then it must be the case that the aces of spades and hearts go to 2 distinct players. And if the aces of spades and hearts go to 2 distinct players, then it must be the case that somebody gets the ace of spades, which is, of course, the entire sample space. Oh, good. So now we have an inclusion relationship. Each of these inclusions is one contained in the other. Let's see if we can parlay this understanding into a simple calculation. So, we're going to utilize a chain rule. We're going to utilize our understanding of these set relationships, these inclusion relationships, and this understanding of how a bridge hand is distributed. Let's start by writing down the probability of the event at hand. Now, the event that every player gets an ace, because of the inclusion relationships, this is the smallest of the 3 events above it. And therefore, the intersection of the 4 events is exactly the smallest of them. And now you look at me and say, oh, this is strange. You want the probability of an event, and now you've complicated it by introducing other things. But wait, there is a method in this madness. The events A of spades, hearts, diamonds, clubs, A of spades, hearts, diamonds, A of spades, hearts, A of spades, stands in the role of 4 distinct events. There happens to be a particular inclusion relationship, which we'll utilize shortly, but there are 4 distinct events. We could just as well have called them A, B, C, and D. We are looking at the conjunction probability of 4 events. That suggests a chaining argument. We can write this as the first event, conditioned upon the occurrence of the last 3, the second event conditioned upon the occurrence of the last 2, the third event conditioned upon the occurrence of the last one, and then the last event. And so here's what our chain rule for conditional probabilities tells us. Oh, okay, it looks like it's getting more complicated. Are we making any progress? I'll pause for a moment. There are certain inclusion relationships. So the event of A of spades, hearts, and diamonds is contained in both A of spades, hearts, and A of spades. And therefore, the side information on the first conditional probability collapses to simply the smallest of those 3 sets, A of spades, hearts, and diamonds. Likewise, in the second of the conditional probabilities, the event A of spades and hearts is manifestly contained in the entire sample space, A of spades. And therefore, the intersection is just the smaller of the 2, A of spades and hearts. Now, here is our problem-specific understanding, which allows us to simplify this complex expression into something which is much more manageable. I now have systems of conditional probabilities, and our question is, in this setting, are these conditional probabilities easy to evaluate? Let's pause and take a look at them one at a time. Let's start at the right. What is the probability of A of spades? Now, A of spades means that somebody gets ace of spades. This is equivalent to the entire sample space because every permutation of your cards will put the ace of spades somewhere. Somebody will get an ace of spades. This is certain. Another way of thinking about this is there are 52 locations the ace of spades can go. Because of the combinatorial symmetry in our probability measure, the ace of spades is equally likely to be in any one of those 52 locations. And therefore, the probability of the ace of spades is just 52 divided by 52, or 1. Okay, that looked easy. Let's take a look at the next one. The probability of the event A of spades and hearts given A of spades. The probability that two distinct players get the aces of spades and the aces of hearts, one apiece, given that some players got the ace of spades. Now let's see what is given. The ace of spades has landed somewhere in the picture. The moment it's landed there, that position is eschewed, is forbidden for where the ace of hearts can land up. Okay, so one of the 52 locations is now forbidden for the ace of hearts. But more, we want the ace of hearts to not just land where the ace of spades is, but it cannot land in any of the 13 cards of the player who has picked up the ace of spades. And therefore, the ace of hearts has got only 39 remaining locations where it can land. The symmetry of the problem tells you that all those 39 locations are equally likely, given that it cannot be in these 13 locations. And therefore, the probability of A of spades and hearts given A of spades is exactly 39 over 51. Remember, one possibility is left out. It's not available anymore. And the remaining 12 cannot be occupied if the ace of hearts has to go somewhere else. Arguing along these lines, the probability of A of spades, hearts, diamonds given A of spades and hearts. If you're given spades and hearts, spades has gone somewhere, hearts has gone somewhere else. Those two locations cannot be where the ace of diamonds lands, so the ace of diamonds has got a total of 50 locations. From 52, you've taken 2 away. But of those 50 locations, 13 plus 13, 26 locations are forbidden. And therefore, there are only 26 locations left for the ace of diamonds to land safely. And so there are 26 out of 50. And finally, the remaining ace of clubs has got only 13 locations left once you place the other 3 aces out of 49 locations. Notice how elegant and simple these conditional probabilities are. Once you understand what exactly the chance creation mechanism is, and putting everything together, we obtain the following. The first conditional probability, 13 possibilities for the ace of clubs out of 49 remaining, having placed the aces of spades, hearts, and diamonds. 26 possibilities for the ace of diamonds, given that out of the 50 possibilities, given that you have placed the aces of spades and hearts. 39 possibilities for the ace of hearts, given out of the 51 possibilities, given that you have placed the ace of spades. And all 52 possibilities for the ace of spades. You evaluate this numerically, and it comes out to about 11%. In a bridge game, very roughly, 10% of the time, in 10% of bridge hands, you'll expect to find that each player has 1 ace. You could try doing this problem directly using enumeration, direct combinatorial methods, and see if you rediscover the answer. It is not at all hard, but the mode of thinking is rather different when you do an enumeration directly along those lines. The idea here is that a proper identification of side information can simplify expressions, can simplify computations.